So what we want to talk about next is a technique that we can use. It's a little bit more flexible. Again, there's kind of more steps that we're going to have to go through, but it allows you to solve a much wider variety of problems when you have multiple variables. Okay, so that is going to be Laplace transforms. How many of you have dealt with Laplace transforms before? A little more than half. Okay. So the idea behind a Laplace transform is we're going to take a problem that's in a certain variable space, right? For this type of problem, it's going to be in the time space or the time domain. And we're going to apply a transform to that so that we actually change the problem from being a representation in time or some function of time to be some function of this alternate dimension that we call the Laplace domain, right? And we often refer to that in terms of the variable s. Okay, so we're just taking some function, we're going to apply a transform to it. It's going to now appear in the domain s. Then we solve it in that domain instead. Okay, and why would we do that? Like, how does that help us? Well, there's a couple of things. So when we apply this transform, if you apply it correctly, you're going to end up taking what would be a PDE in time and making it an ODE in S, right? If you have an ODE in time, you make it a constant or just a single normal function in S, right? So you're kind of reducing the order of the solution that you get, and then it makes it easier to solve it. Right? You have more tools available to solve that problem in S than you do in T. Okay, once you solve that problem in S, then you have to get it back into time. So there's several ways to do that. Inverse Laplace transform is a thing, and we'll talk about that. But there's also numerical tools that you can use. And actually, the homework that you're going to do next week is going to involve getting a problem into the domain S, solving it there, and then using a numerical technique to get it back into time. Okay. So there's just kind of three steps here. One, take the Laplace transform of whatever your ODE is and put it in the S domain. Two, solve the problem in S. And then three, take the inverse, right? So kind of straightforward, but there's a bit more to it, right? Let's see. Okay, so let's keep up here. Okay, so let's take a little quick example for the Laplace transform. So let's say we have a function. So a function in time. Let's say it's some function is a function of time. Some f is a function of time. So just in terms of the nomenclature we're using here, if we take the Laplace transform of that, we would write it as the following. So Laplace transform, that's going to be written with these angle brackets or sort of half triangles. So it'd be like this. This is the operation of taking the Laplace transform. So you'll see that kind of up here. The Laplace transform itself, so this is what the Laplace transform operation. The Laplace transform itself, function, would be written as f hat of s. Okay, so we take some f of t, we apply this Laplace transform operation, and we end up with a new function, f hat, which is in a different domain, right? So we have to differentiate it somehow between t and s, and so you'll see the hat appear. Okay, so for a problem with temperature as a function of time, once you transform it into the s domain, you'd write it as t hat instead of just plain t. Okay, just so you always want to keep track of where you are. Okay, so let's do a quick example here. So I'm going to say my function of time, I'm going to take the Laplace transform of that function of time. I'm going to write it as f hat of s now. And the actual definition of the Laplace transform is seemingly kind of random, but there's a reason to it. It's the integral from 0 to infinity of exponential of minus s times t times whatever your function is a function of time, dt. Okay, so what are we doing here? We're taking the transform is the integral of the exponential minus st. That's always the same. The thing that changes based on your case is whatever f of t is. Okay, it could be a constant, it could be some whatever function of time that you have. But you do this integral and you integrate over all of t, and then t goes away, right? And you're actually just left with s. And it's kind of, you have to stare at this for a while to kind of see why it works. But if you do this, you end up with just a function of s, and it reduces from, say, a PDE to an ODE to just a regular equation. So, for example, let's do this. Let's say my function of time is some constant. Right? That's a function of time. It's just not changing with time, right? So let's do this example. So let's take the Laplace transform of my constant. Okay, so if we plug that in, it's going to be the integral from 0 to infinity of exponential minus st times constant, or our function of t, times dt. So for this example, we can pull the constant out of the integral, and we end up with 0 to infinity exponential of minus st dt. Okay, the integral of this is minus c over s, right? We have to take, do the chain rule, we're taking out the minus s and dividing by that. So minus c over s times the exponential of minus st. And that's evaluated from at 0 and evaluated at infinity. Okay, and then finally we can evaluate those and we get minus c over s. Right, so exponential of minus s at infinity minus exponential of minus s times 0. Right, and this just gives us c over s. Okay, so for this example, I mean, this is just showing how the transform works in a really simple case. Does this really help us in reducing the complexity of the problem? Like this example, not really. Okay, but you can at least kind of see how things work. Now, as you go through and you have more complicated functions of time, that becomes more interesting, right? The integrals become more interesting. But for now, this is at least functionally how this works. Okay, so let's look at some common transforms. This little bit of an eye chart here. Let me kind of zoom in. So this is from the book. You can look these up pretty much anywhere, see these kind of tables. But the idea is, let's say you have some function that appears as a function of time, and you want to know how to transform that into the S domain. You can just go to these tables. I mean, first of all, you could do this in Maple if you wanted to, or do it by hand if you wanted to. But these exist everywhere. So just go to these tables and you can try to just pattern, what does my function in time look like? And then here's what the corresponding thing in S would be. So here we just did C and we decided it was C over S, right? Okay, good, we did that right. Let's say our function of time is some constant times time, right? Well, then this becomes C over S squared. Let's say it's, right, so on, sine becomes this. So you can kind of just match the pattern and go through and pick out what makes sense. The other thing that I want to point out is, well, you can do this in Maple, right? So we could, let's actually go to Maple real quick and look at this. Let's see here. Okay, so we can do these things in Maple. The thing you need to do in Maple, though, first is you have to actually load the library. So by default, the Fourier library is not loaded. So you do that with this function with int trans, and it loads a bunch of stuff, including the Fourier stuff. But this will then kind of make these commands available. If you don't do this, it'll complain that it doesn't know what Laplace is. Okay, so to do a Laplace transform in Maple, we would just use the command Laplace, and we're going to take, let's do our constant first. So this is just some constant. And it goes, the function you're transforming, then the domain you're transforming from, and then the domain you're transforming to. So we're going from time to S. And you can see here, yeah, it worked. Okay, let's say we had a little more interesting function, sine omega t. We want to go from t to S. We get omega over, this is the transform you get from that table. Okay, so let's sit there for a second. The other thing that is important to understand is some of the properties of Laplace transforms. So this little table here gives you a list of properties or characteristics of Laplace transforms. So the first one here says that, this one here, this one says that if I have two functions of time, and I take the Laplace transform of those two functions that are adding together, you can take the Laplace transform separately, right, and then add them back together. Okay. This second one says if I have some function of time times a constant, and I take the transform of that, then I just end up with the transform in S. Okay. So these, you kind of look at them and stare at them now, and it isn't clear how you're going to use them. But once you get into an actual problem, it'll become clear. You have to go through and kind of pick out which one you want to use, and then pull them together. The third one here says, and this is kind of the most powerful one, like this is the most valuable one that you really have. So what this is saying is I've got some derivative of temperature with respect to time, right? Not position, with respect to time. I can transform that to be this equation, right? You can see there's no derivative in that equation, right? So we're reducing the order of that derivative down to some equation in just S. That's not a derivative. So you're making the problem simpler to solve. If you have a derivative with respect to x and time, then it becomes this function. If you have a derivative with respect to just x, right, which we're not quite there yet, we're going to get to the 1D problems later, but if you do have just a derivative with respect to x, then it just becomes that derivative again in the S domain. Okay, so just keep these handy. Like for the exam, this would be something I would give you, like these tables, and you just need to know how to use them. Okay.